Hello Calculus folks, this is Mr. McAllen and today we're going to talk about lesson 2.1, the second day. This is where we're going to actually talk about limits, and we're going to talk about one-sided versus two-sided limits, and we're going to talk about both a graphical and a numerical approach. And this is basically recap what we did in class. So the first thing we started off with in class was we gave you guys a do now, and in this do now we were asking, using this graph below, to evaluate the limit as x approaches 2. After doing that, we want you to evaluate the function at the value 2. So I'll pause the video and let you answer that, and then when I come back I'll share the answer. Okay, so hopefully you had a chance to do this, and if we're doing the limit as x approaches 2, what we want to think about is as we approach from the left and we approach from the right on the x-axis, see how we're approaching towards 2 from the left and towards 2 from the right, we see that the function value is heading to a value of 1. So the limit would be equal to 1. Now, that's totally different than what the function value is at 2. The limit describes where the function is heading. The function value tells you what the function is actually equal to. So the function value at 2, if you go vertically up till you hit the function, which is right here, we have a value of 2. So in this case, you can clearly see that there is a way that your limit can be completely different than your function at the same value as where x is approaching 2 and the function is evaluated at 2. Moving along, the next thing we talked about in class was we talked about one-sided limits with piecewise functions, and we also talked about some algebraic work, including how do we evaluate, or how do we know, this is a special limit in our textbook, where we have the sine of x over x, and as x approaches 0, we define it as equaling the value 1. Well, first of all, we want to show why that is that value, but also we need you to remember that and know how to manipulate limits with that. So in class, what we first did to kind of warm up and get going was we just did a regular limit, and we stressed the importance of Theorem 2. In our textbook, it's referred to as Theorem 2. And so Theorem 2 basically said you're allowed to plug in to evaluate limits. So what we're going to do here is we'll just plug in. So we'll have 2 squared plus 5 times 2 plus 6 all over 2 plus 2. And this limit will equal 4, 10, 16, 20 over 4, which the limit is going to the value of 5. So the important thing here is to remember that when you're evaluating a limit, and once you start plugging in that y value, you don't need to write the limit in front of it anymore, because when you're evaluating a limit, we understand that you are plugging that value in. But in our next problem, one of the problems from the book, number 25, we experienced what happens when the limit does not work out so nicely with plugging in. So I'll just write up here, I'll do the limit as x approaches 1. We have x minus 1 over x squared minus 1. And when you first try Theorem 2 and plugging in the limit, you find out that you end up getting 1 minus 1 over 1 squared minus 1, which is 0 over 0. Now, under most circumstances, when you get a does not exist scenario, you're supposed to do some algebraic manipulation. So one of the algebraic manipulations for this, or the only one, is really to factor the denominator. And upon factoring, we see that a term cancels within the top and the bottom. I'm going to now just rewrite the limit as x approaches 1, and on the top I have just the 1 left over from the cancellation. I have x plus 1. Now notice I rewrote limit. I'm saying as x goes to 1, but in the next step I can evaluate the limit and not write the limit symbol anymore. So I have 1 over 2, saying that my limit heads to 1/2. if you look at some of the other problems we have in the exercises, you can see that a variety of them would use a factoring approach. Here we have factoring of cubes, or difference of cubes. Here we have, in the numerator, we would try to add the fractions. So simple manipulations may make the limit algebra work out to be much easier than it is. So, but then we have this ugly, ugly problem with sine of x. How do we handle sine of x in our limit problems? Well, we need a key ingredient, and that's what we went over in class. We talked about how the limit as x approaches 0 of sine of x over x is really equal to 1. We showed this graphically using Desmos, and what we showed was that when x is approaching 0, we have the sine function. Oops, that's not a very good sine function. And we had the function y equals x, just the linear function. And as x approaches 0, you can see that the two functions, sine of x and x, are lying on top of each other, indistinguishable. And as a result, because they're the same exact value as x goes to 0, we can argue that the division of these functions would equal 1. In fact, a common term or a common approximation used in physics is physics teachers will tell people when they're solving certain types of questions on whether it be a pendulum equation or something to do with simple harmonic motion, they allow students to make, whenever they see the sine of x, to approximate it to be x, as long as x is not too large, as long as x remains small. And that's the same idea as what's going on here. Anyway, moving along with a lesson from yesterday, or from lesson 1.2.1, the next thing we came across was the idea of two-sided limits, one-sided and two-sided limits. So we have a left hand and a right hand limit, and what this does, it helps us figure out if a limit actually does exist. If the left hand limit does not equal the right hand limit, then you cannot say, or you can't say, well, yeah, you can't say that the limit as x approaches a even exists if the left hand limit and the right hand limit are not the same. I should say that's C, because that's to be consistent with a book. So, moving along, we have a piecewise function that we looked at earlier in the lesson, and I set up for all the kids this exercise so that we could look and see what the different function values are at different x values and what the different limits are. So when we fill this out, first we have the students fill out the function values. So I'll fill those out right now. So f of 1 is equal to 1 right here. F of 0 is equal to 1 right there. And f of 2 is equal to 2 up at that point there. But when we do the limit from the left of f of x, if we're coming in from the left, you could see here from the left of 1, this limit is heading to 0. When we come in from the right, you can see that this limit is equal to 1. And when you see the combined limit, the whole limit, we would have to say that that does not exist, because the limit from the left doesn't equal the limit from the right. You try the other 6 and tell me what you think about those sets of limits, and I'll pause the video so you can do that. Okay, so I'm back, and the values for these limits, as x approaches 0 from the right, that's going to be equal to a 1 value. As x approaches 0 from the left, that value does not exist because there is no function over here. And as you approach x equals 0 from both sides, because the left-hand side doesn't equal the right-hand side, you would say that this limit does not exist either. The answers over here on this side are going to be x approaches 2 from the left is going to equal, let me just erase this, is going to equal 1. The limit from the right is going to equal 1. And the limit as a whole will be 1. So in this case, the limit does exist because the left and the right hand side both are the same. The last point for today was we worked with piecewise functions. So on piecewise functions, these are actually really easy to evaluate limits because the prescription as far as what we use is already set up with our inequalities. For example, the limit as x approaches 2 from the left. So which function of the 5 would be 2 from the left? It would be this one, because that's where x is less than 2. So we would plug into this equation, which is not too exciting. We would plug in the value of x equals 2, and we would get the value of 1, because it's a constant function. When we use this limit up here, 2 from the right, we would use this inequality and this function to plug into using Theorem 2, and we would end up getting 2 minus 1, which would equal 1. This answer from before is also 1. As a result, does our limit exist as a whole limit? And it does, because it's both equal to the value of 1. Hopefully this video has helped piece together some of the things that we went over in class, and I'm just showing here what we also did as exercises, but we basically just did some more exercises to show basically do some extra practice in class after we got done with the lesson. So if you have any questions, of course, if you missed class, please ask, but after you watch this video, hopefully the missed points will become more clear to you than they were before. Look forward to hearing your comments.